Hi, good morning. Just to recall what we have discussed in our last two classes. We have discussed the definition of linear transformation. Now, what do you mean by a linear transformation? A linear transformation is a map T from V to W which satisfies the condition T of C alpha plus beta equal to C into T alpha plus T beta. Also, we have discussed some examples of linear transformation. Okay, today we are going to discuss some definitions of null space of a linear transformation, range of a linear transformation. Also, we are going to discuss one of the most interesting theorem, rank nullity theorem. Okay. Now, what do you mean by a null space of a linear transformation? Let V and W be vector spaces over the field F and let T be a linear transformation from V into W. Then the null space of T is the set of all vectors alpha in V such that T of alpha is equal to 0. Okay, this is the definition of null space of T. Okay. Therefore, actually null space of T set of all alpha belongs to V such that T of alpha equal to 0. Now we are going to prove one result. The null space of T is a subspace of is actually subspace of V. Subspace of V. Okay. To prove subspace of V, it is we have to prove we have one result. A non-empty subset W is a subspace if C alpha plus beta belongs to W for every alpha comma beta belongs to V and for every alpha comma beta belongs to W and scalar C belongs to F. Okay. Now we have n of t is equal to set of all alpha belongs to V such that t of alpha equal to 0. Set of all alpha belongs to V. Therefore, clearly this is a subset of V. Okay. Now we know that t of 0 equal to 0. Okay. Therefore, t of 0 equal to 0. We have one property. Okay. Therefore, clearly 0 belongs to n of t. Therefore, n of t is a non-empty subset of V because 0 belongs to n of t. So now you are take two elements alpha comma beta belongs to n of t. Then alpha belongs to n of t means t alpha equal to 0. Beta belongs to n of t implies t beta equal to 0. Now t of c alpha plus beta equal to by definition this one. Okay, and that's equal to c into 0 plus 0 is equal to 0. This implies c alpha plus beta belongs to n of t. Thus we get n of t is a non-empty subset of V and which satisfies this condition. This implies n of t is a subspace of V. Okay. Now, now we get thus we get n of t is a subspace of V. Okay. So if V is a finite dimensional space, then dimension of null space of T is known as nullity of T. Okay, dimension of null space of T is a subset of V. Okay, therefore if V is finite dimensional, then dimension of n of T is also finite dimensional and that dimension is called nullity of T. Okay, now moving to the definition of range of a linear transformation. Let T be a linear transformation from V into W, then range of T denoted by R of T or RT is the set of all vectors beta in W. T is a linear transformation from V into W and range of T is set of all vectors beta in W such that beta equal to T alpha for some alpha in V. Okay, therefore our range of T, the notation R of T equal to set of all T alpha belongs to W such that alpha belongs to V. Clear? N of T is set of all alpha belongs to V. Okay, such that T alpha equal to 0. This is a subset of V. But range of T is set of all T alpha. T is a map from V to W. So T alpha clearly belongs to W and T alpha such that alpha belongs to V. This is a subset of W. Now we are going to prove R of T is a subspace of W. Here W. Okay. This is W. Okay. So we have R of t set of all t alpha belongs to W such that alpha belongs to V, and clearly this is a subset of W. Okay. We have t of 0 equal to 0, and this 0 belongs to W because W is a subspace. Therefore clearly 0 W is a vector space, therefore 0 belongs to W, and this 0 is actually an image of a 0. Okay, image of a this 0 belongs to V, and T of 0 equal to 0. T of some element equal to 0. Therefore, this belongs to range of T. Okay, therefore, range of T is a non-empty subset of W. Now we have to prove the same result. Okay, so you take two elements beta 1 and beta 2 belongs to R of T. Now by definition, beta 1 belongs to R of T means there exists a alpha 1 belongs to V such that T alpha 1 is equal to beta 1. Beta 2 belongs to R of T implies there exists a alpha 2 belongs to V such that T alpha 2 equal to beta 2. Okay. Now for any C belongs to F, C beta 1 plus beta 2 equal to, we have to prove this belongs to R of T. For proving R of T is a subspace. Okay. This you can write like this. And as T is a linear transformation, you can write like this. Alpha 1, alpha 2 belongs to V. V is a vector space. Therefore, this belongs to V. Okay. T of some element in V, clearly that belongs to W, and T of some element that is belongs to R of T. Okay. Therefore, T of C alpha 1 plus alpha 2 belongs to R of T. That implies C beta 1 plus beta 2 belongs to R of T. Thus we get, as beta 1 beta 2 are arbitrary, we get R of T is a subspace of W. Okay, thus we get N of T is also a subspace of V, and R of T is a subspace of W. Okay, now as in the previous case, here also, if V is, sorry, okay, if V is finite dimensional, then the dimension of range, if V, okay, W, okay, if V, W is finite dimensional, then the dimension of range of T is known as rank of T. Okay. V or W. This I will verify. I think it is V. If V is finite dimensional, then we have to check whether range of T is also finite dimensional. Okay. Okay. Then the dimension of range of T is also known as rank of T. Okay. If V is finite dimensional, then the dimension of range of T is known as rank of T. Now, we are moving to the theorem, and theorem is known as rank nullity theorem. I think you have already studied this. Now let V and, now what is theorem? Let V and W be vector spaces over the field F, and let T be a linear transformation from V into W, and suppose that V is finite dimensional. Then rank T plus nullity of T equal to dimension of V. Clear? T is a map from V to W. Okay. And V is finite dimensional. Then we have to prove range of T plus rank of T plus nullity of T. Okay. This is actually space, therefore dimension. This is also dimension of this space plus dimension of this space is equal to dimension of V. Okay. Proof is very easy. You have to remember only one thing, first condition. Okay, so we are moving to the proof. Given that V is finite dimensional, okay, let the dimension of V equal to n. Clear? Given V is finite dimensional, and suppose dimension of V equal to n. Now we know that n of T, null space of T, is a subspace of V. Okay, therefore n of T is also finite dimensional because V is finite dimensional. Okay, let the dimension of null space of T be K. You have to remember this thing. Okay, all other things automatically will happen. Okay, dimension of null space of T equal to K. That is nullity of t equal to k. So, what is the meaning of that? Dimension k means there exists a basis consisting of k elements. Let alpha 1, alpha 2, etc. alpha k be a basis of n of t. Okay. Now, basis means this is a linearly independent set in n of t actually. Okay. And it is also linearly independent in V. Okay. So this is a linearly independent set in V implies they form a part of a basis for V. We have that result. Any linearly independent set form a part of a basis. Okay. Therefore, if you take some B equal to alpha 1, alpha 2, etc., alpha k plus 1, etc., alpha n, and let it be a basis for V containing these elements. Clear? These form a they form a part of a basis for V. That means we have a we has a basis consisting of alpha 1, alpha 2, etc., alpha k. Let it be this B. Okay. Now, these elements are elements of n of t. That means these are bases for n of t. That means clearly they belongs to n of t. Okay. Therefore, alpha 1, alpha 2, etc. alpha k, these elements clearly belongs to n of t. That means t of alpha 1 equal to 0, t of alpha 2 equal to 0, etc. t of alpha k equal to 0. Now consider the vectors t alpha k plus 1, t alpha k plus 2, etc. t alpha n. Clearly, these belongs to range of t because alpha k plus 1 belongs to V. Therefore, t alpha k plus 1 belongs to range of t. Okay. Now we are going to prove this set form a basis for R of t. For this, first we have to prove this set spans R of t. Clear? So spans R of t means if you take any beta belongs to R of t, you have to prove beta can be expressed as linear combination of these elements. Okay. So let beta belongs to R of t. Now beta belongs to R of t means there exists a alpha belongs to V such that t alpha equal to beta. But B is a basis for V and alpha belongs to V. Therefore, this alpha you can write as linear combination of elements of B. That means there exists a scalar C1, C2, etc. such that alpha equal to this one. Now, what is T alpha? T alpha is T of this one. Okay. So, using linear properties C1 T alpha 1, C2 T alpha 2, etc. CK T alpha k, etc. This one. But T alpha 1 0, T alpha 2 0, etc. up to T alpha k 0. And this equal to this one. This implies this one. That means our T alpha is a linear combination of T alpha k plus 1, T alpha k plus 2, etc. T alpha. That is beta can be written as linear combination of this one. As beta is arbitrary, we can say that any vector you can write as a linear combination of these elements. That means this set spans range of T. Clear? Now we have to prove this set is linearly independent. Okay. For this, you take some constants. I am denoting this as Ck plus 1, Ck plus 2, etc. Cn T alpha k plus 1, T alpha k plus 2, etc. equal to 0. Now using again linearity property T of this one equal to 0. This implies T of something equal to 0 implies T of alpha equal to 0 implies alpha belongs to n of t. Okay. Therefore, this element belongs to n of t. Okay. Now, we know that alpha 1, alpha 2, etc. alpha k is a basis for n of t. Therefore, if you take any alpha belongs to n of t, that alpha can be written as linear combination of this element. Therefore, here we have this is equal to, because this belongs to n of t, therefore this you can write as linear combination of alpha 1, alpha 2, etc. alpha k. And coefficients I am marking as c1, c2, etc. ck. Now if you take this to right side, we get c1 alpha 1 plus c2 alpha 2 plus etc. plus this one equal to 0. But we know that alpha 1, alpha 2, etc. Alpha n is a form a basis for V. Therefore, they are linearly independent, and some linear combination equal to 0 implies all the coefficients is equal to 0. Thus, we get Ck plus 1, T alpha k plus 1, etc. plus Cn alpha n equal to 0 implies coefficients equal to 0. Therefore, this set is linearly independent. Okay, this set is linearly independent. Here we get this set is spans range of T. This set is here we get this set is linearly independent. Therefore, this form a basis for R of T. Now, what is rank of T? Rank of T means number of elements in the basis. How many elements are there? 1, 2, 3, etc. up to this one. This is n. Okay, so n is equal to some k plus some m. You can write like this. Okay, so what is n actually? What is n actually? This number. This number is actually m is equal to, you can write as n minus k. Once again, here what about the number of elements? If you consider 1, 2, 3, etc. up to k, etc. up to n. How many elements are there from k plus 1 to n? Number of elements is n minus k. Okay, therefore this number is actually n minus k. Therefore, rank of T is dimension of range of T, which is equal to number of elements in the basis of range of T, and that's equal to n minus k. But we know that n is equal to dimension of V and k equal to nullity of T. Therefore, if you take this to left hand side, we get rank T plus nullity of T equal to dimension of V. And this is known as rank nullity theorem. Okay, clear? Here we first took basis for null space of T, starting with this set. And this, as this is a basis, this is a linearly independent set in V. Therefore, we can construct a basis containing this one. Then consider T alpha k plus 1, T alpha k plus 2, etc. T alpha, and we are proving this form a basis for R of T. Okay, hope this is clear.